The floor inside this house is cold. Not cool, cold. The kind of cold that comes up through the soles of your shoes on a July afternoon, when the thermometer outside is reading 94 degrees and the air in the yard feels like the inside of a clothes dryer. I am standing in the front room of a farmhouse outside Millersburg, Ohio, and the surface under my feet is drawing heat out of the room. The way a cast iron pan draws heat out of whatever you set on it. There is no air conditioning in this house. There is no fan running. The windows on the south wall are closed, and the interior temperature, measured with a simple analog thermometer, reads 68 degrees. In July, in Ohio, I looked at that thermometer for a long time before I trusted it. The floor is stone, not tile over concrete, not engineered hardwood over a subfloor, not any material you would find in a box store. It is dry-laid limestone flags, 2 to 4 inches thick, set directly on a bed of compacted sand and fine gravel that sits on undisturbed subsoil. No adhesive, no vapor barrier, no concrete underlayment. The stones are not sealed. They are not finished. They are not level in the way a modern floor contractor would consider acceptable. They are level the way land is level, functionally, without perfection. And they are keeping this house 68 degrees on a 94-degree July afternoon without consuming a single watt of electricity. The Amish family that owns this house has lived in it for 4 generations. The floor was laid by the great-grandmother of the current owner in 1921. 103 years of passive cooling. No compressor, no refrigerant, no monthly utility surcharge, no service call, no system to maintain. Just stone, sand, subsoil, and physics, so straightforward that once you understand it, the question stops being why the Amish still do this, and starts being why the rest of us ever stopped. Stay with me, because the answer to that second question involves a number, a lobbying campaign, and a building code change. That happened in 1955 that you were never supposed to hear about. Here is the physics first, because this only seems mysterious until you understand what is actually happening. The ground temperature at 3 to 4 feet below the surface in most of the continental United States stays between 50 and 60 degrees Fahrenheit year-round. Not in winter, not in summer, year-round. It does not matter if the surface temperature swings from 10 degrees in January to 100 degrees in August. Below 3 feet, the Earth is a thermal battery that has been charging for 10,000 years and does not fluctuate with the seasons. This is not a theory. It is a measured, documented physical constant that geothermal engineers rely on every day to design heat pump systems. That cost $40,000 to install. The Amish rely on the same constant. Their installation cost is the labor to lay stone. A dry-laid stone floor with no vapor barrier, no adhesive layer, no sealed concrete between it and the subsoil is in direct thermal contact with that ground mass below. The stone itself, limestone, sandstone, or fieldstone, has a thermal conductivity and a heat capacity that allows it to absorb heat from the room above and conduct it downward into the cooler earth continuously. The room gives heat to the stone. The stone gives heat to the ground. The ground absorbs it into a thermal mass so large it does not register the load. The result is a floor surface that stays between 58 and 64 degrees Fahrenheit on the hottest summer days. And a floor that cold is not just comfortable to walk on. It is actively cooling the room above it through radiant heat exchange. The same principle a cold glass of water uses to condense moisture from the air around it. The cool surface pulls thermal energy from the warm air above it continuously, without a compressor, without a refrigerant cycle, without any mechanical process at all. This is passive cooling at the most fundamental level. The ground is the system. The stone is the interface. The absence of barrier between them is the entire engineering decision. The woman who owns this house is named Hannah. She is 67 years old. the granddaughter of the woman who laid the floor in 1921. She has lived in this house her entire life. She has never owned an air conditioner. She said this not as a point of pride, the way someone who has recently discovered minimalism might say it. She said it the way you would say, you have never needed a second refrigerator. It simply has not been necessary. I asked her what the hottest summer she could remember was. She thought for a moment and said the summer of 2012, when the heat index outside reached 107 for 11 consecutive days. I asked her what the temperature inside the house was. She said she did not know exactly. She said it was comfortable. She said her children played on the floor because the floor was the coolest place. And the children knew it without being told. Then she said something that I wrote down immediately. She said the floor had never been a temperature management system to her family. She said it was simply the floor. The cooling was not the point of it. The point of it was that it was a good floor. Durable, repairable, local material, zero maintenance. And the cooling was what happened naturally when you built a good floor correctly. That is the sentence that stayed with me for the drive home. And for a week afterward, the cooling was not the point. The cooling was what happened when you stopped fighting the physics and let the material do what materials do. The modern construction industry has been fighting that physics for 70 years and charging you every month for the fight. Before I show you exactly how the floor is built, I need to tell you about what replaced it. Because the dry-laid stone floor did not disappear from American home construction. Because something better came along. It disappeared because something more profitable came along. In the years immediately following World War II, the American residential construction industry underwent the fastest standardization in its history. The GI Bill generated an enormous demand for new housing, and the response was the production home. Built fast, built cheap, built to a standard that could be replicated by semi-skilled labor at scale. Concrete slab foundations became the dominant floor system for new construction in warm climates. Poured concrete subfloors with adhesive down flooring became standard everywhere else. Concrete slab, sealed and poured, is thermally isolated from the ground below it. The concrete itself has a different thermal profile than stone. It holds heat rather than conducting it, which makes it comfortable in winter but actively uncomfortable in summer. A sealed concrete slab in a hot climate absorbs and stores solar and ambient heat, turning the floor into a radiant heat source rather than a heat sink. Then the air conditioning industry arrived, and a floor that stored heat rather than releasing. It was a floor that made air conditioning not a luxury but a necessity. Between 1950 and 1970, central air conditioning installation in American homes went from roughly 1% to over 30%. By 1980, it was above 50%. The construction standards that made sealed concrete the default floor system and the air conditioning industry that profited from the resulting heat problem grew up together, fed each other, and between them created a dependency that now costs the average American homeowner between $1,500 and $3,000 per year in cooling costs. The International Residential Code, which governs residential construction in most of the United States, requires a continuous vapor barrier under all concrete slab floors. That requirement was codified in its current form in 1955. The vapor barrier is what breaks thermal contact between the slab and the ground below. It is sold as a moisture management tool, and it does manage moisture. It also eliminates the passive cooling effect of ground contact completely. One layer of 6 mil polyethylene sheeting, less than a penny per square foot of material, and it severs the connection between your floor and the 55-degree earth. 3 feet below it permanently. The people who wrote that code provision in 1955 were not stupid. They understood what they were doing. Here is how the floor is built. The Amish version. The one that has been keeping Hannah's house 68 degrees in July for 103 years. The process begins with the subsoil. In the traditional Amish construction method, The floor is not built on top of an existing foundation. It is built on the ground itself. The first step is excavation, removing topsoil and organic material until you reach mineral subsoil, typically 12 to 18 inches below grade. Organic material holds moisture and compresses over time. Mineral subsoil does neither, providing a stable base. The excavated area is compacted by hand. The Amish use a heavy, flat-bottomed hand tamper, lifted and dropped repeatedly until the soil no longer gives underfoot. Compaction takes a half day for an average room. It is physical work, the only part requiring significant labor. Everything after it is placement. On top of the compacted subsoil goes a layer of coarse, angular gravel between 3/4 of an inch and 1.5 inches. These angular edges interlock under compression, resisting lateral movement. This 4 to 6 inch layer provides drainage for moisture migrating upward from the subsoil. It disperses moisture rather than accumulating under the stone and provides a stable level base for the stone flags above. On top of the gravel goes a 2 to 3 inch layer of clean, coarse sand. This is the setting bed. Stone flags are set into this sand, adjusted for level, and tapped into position with a rubber mallet. The sand conforms to irregular bottom surfaces. This allows individual flags to be lifted and reset if one cracks or settles. A floor is fully repairable without tools or professional help. No concrete, no adhesive, no vapor barrier. Nothing between the stone and the earth except gravel and sand in full thermal contact with the subsoil. Stone flags are selected for thickness and density, with 2 to 4 inches being the traditional target. Thicker than that, thermal mass becomes too large. The floor stays cold in winter as long as it does in summer, creating a comfort problem. Thinner than 2 inches, and flags crack under foot traffic. 2 to 4 inches is the thermal and structural optimum, converged upon by 300 years of Amish floor laying experience. The stone species matters. Limestone is preferred in Ohio, abundant locally, with high thermal conductivity to efficiently conduct heat between room and ground. It's low enough to feel comfortable underfoot, unlike aggressively cold polished granite. Sandstone is used where limestone isn't available. Fieldstone works structurally, but has inconsistent thermal properties. Old-timers in Holmes County and every Amish floor layer agree, limestone is best. Joints between flags are left open or filled with clean sand. No grout, no mortar. Open joints allow moisture vapor to pass upward, then dissipate. This prevents moisture accumulation and mold. It also allows the floor to expand and contract with temperature changes without cracking. The floor breathes. That breathability is not aesthetic. It's a sophisticated moisture management strategy, superior to any vapor barrier under a concrete slab. The floor's layout within the house follows a specific orientation principle, often missed in passive cooling discussions. This detail separates good cooling from exceptional. The floor is thicker under the south-facing rooms. Flags for south-facing rooms, receiving more direct solar load, are chosen from the thicker end, 3.5 to 4 inches. North-facing rooms with less solar load use thinner flags, 2 to 2.5 inches. Thicker flags have greater thermal mass. They absorb more heat before their surface temperature rises, giving longer cooling duration before conducting heat downward into the ground. The Amish didn't derive this from modeling programs, but from generations of observation, noticing which rooms warmed first and selecting heavier stone. The result is a passive thermal gradient built into the floor, responding to the house's solar geometry without active control. There's a 4-inch thick, 22-inch wide limestone flag in Hannah's south parlor. Her great-grandmother selected it specifically for that room in 1921. Hannah knows this because her grandmother told her. One woman's material intuition in 1921 still regulates that room's temperature in 2024. There's a second element working with the floor. Almost no one outside these communities connects to cooling performance. The wall construction. Traditional Amish farmhouses in Ohio have walls thicker than modern residential construction, 18 to 24 inches of mass construction. Mass walls behave thermally like mass floors. They absorb heat during the day, buffering the interior from peak outdoor temperatures. They release stored heat slowly overnight, when it can be vented through opened windows. The combination of a mass floor and mass walls creates a building envelope that is essentially a thermal flywheel. The interior temperature doesn't track exterior temperature in real time. It lags by 12 to 18 hours. On a day when outdoor temperature swings from 65 to 94 degrees, the interior never experiences the peak. It experiences a smooth version, perhaps 72 degrees at the high point, because the mass absorbs the peak and releases it after the exterior cools. The floor is the anchor of this system. The walls amplify it. The combination produces 68 degrees in July with no mechanical cooling. Modern light frame construction has almost no thermal mass. Interior temperature tracks exterior temperature within an hour of any change. The air conditioner is not supplementing a thermal management system. It is the only system. Remove it, and the house becomes outdoor temperature in 90 minutes. That is not a design. That is a dependency. And it was built into the standard construction method of American residential housing deliberately, gradually, and profitably. I want to tell you about a third person. His name was Levi Hirschberger, from Charm, Ohio, a finish carpenter and floor layer. He had installed dry-laid stone floors in 11 Amish homes over 30 years. He was a craftsman who did this specific thing and had opinions about every variable. I asked him the most common mistake when building this floor without tradition. He didn't hesitate. He said the sand. He said people used the wrong sand, fine masonry sand, instead of coarse, sharp sand. Flags settled unevenly because fine sand compressed and migrated. He had relaid 3 floors because the original builder used fine sand. He had never relaid a floor because of the stone. I asked him what he'd tell someone building this floor for the first time. He said 3 things. Compact the subsoil until your feet feel nothing. Use coarse, sharp sand, not mason sand, not play sand, not anything that feels soft in your hand. And do not rush the setting. He said each flag needed to be set, tested underfoot, and adjusted before the next one went in. He said a floor laid in a hurry showed its hurry within 5 years. A floor laid with patience lasted 100. Then he said something I'd been thinking about since I drove out of his county. He said the floor was the easiest part of the house to build if you did it right. He said it was the hardest part to fix if you did it wrong. And he said the difference between right and wrong was not skill. It was attention. Attention, not a degree in material science, not a licensed contractor, not a $40,000 geothermal system. Attention to the subsoil, attention to the gravel grade, attention to the sand, attention to each flag as it went down. That is the entire engineering specification of a system that keeps a house 68 degrees in July without consuming a single watt of electricity. Here is what I want you to do this weekend. I want you to go into your basement or crawl space, if you have one, and find out whether you have a vapor barrier under your concrete floor or slab. If you have a poured concrete slab on grade, that vapor barrier is required by code, and it is there. If you have a crawl space with exposed earth, you may have more options than you think. Write in the comments what kind of floor system your house has. Slab on grade, crawl space, basement with poured floor. And tell me your climate zone, your state, and whether you are in a hot summer region. Because I am building a resource for this community that maps the passive cooling potential of different foundation types by climate zone. The ground temperature at 3 feet depth in your county is a public record. Your local cooperative extension service publishes it. And that number plus your current foundation type tells you exactly how much passive cooling capacity you have surrendered. to a building code that was written in the same decade the air conditioning industry went national. If you have ever been in a building, old farmhouse, stone barn, root cellar, church basement, where the floor was noticeably cooler than the outside air on a summer day, I want to hear about it. Tell me where it was, what the floor was made of, and what the temperature difference felt like, because I am collecting those accounts. And I am going to show you the pattern in them that nobody in the construction industry wants to name out loud. The floor Hannah walks on every July was laid by a woman born in the 19th century who never heard of an HVAC system and never needed one. That floor has outlasted 7 American presidents, 2 world wars, the invention of the microchip, and the entire arc of the modern air conditioning industry. It will outlast the next 7 presidents, too, and the next generation of HVAC technology and every energy price spike that comes between now and then. Because the ground temperature 3 feet below that floor has not changed in 10,000 years. And it is not going to change because the utility rate went up. You do not need a compressor. You do not need a refrigerant cycle. You do not need a thermostat or a service contract, or a filter replacement schedule or a monthly bill. You need stone. You need sand. You need subsoil that has been cold since before your great-grandmother was born. And you need the patience to lay each flag the way Levi Hirschberger laid his, one at a time, tested underfoot. 68 degrees Fahrenheit in July. Next week, I am going to show you the Amish masonry stove that heats that same house through an Ohio winter on 1 cord of wood. A heating system so efficient that the natural gas industry commissioned 3 separate studies between 1962 and 1978 trying to find a flaw in it. They found none, and they buried all 3 studies. Hit subscribe, because the numbers in that one are going to stay with you a long time.